Hello everyone, and welcome to Derivative Examples 2. So in Derivative Examples 1, I introduced to you differential calculus, and we saw how powerful it was that we could take a function, say a function of position and time, and instead of just calculating a single slope of a tangent line at some point, we could actually find all the slopes, right? We could find the entire velocity function simply by taking a derivative. And I taught you a few of the rules for basic derivatives. We're going to use those again today, but before we do here, I want to cover some little more complex kind of graphing that you're likely to see on an AP test. So say we have an object whose position versus time function looks like this. So here's a graph of it. Right? You can see some curvy parts and you can see some straight parts. And I want to create the corresponding velocity time and acceleration time graphs that go with this. It's a pretty typical thing to be asked to do at various points on an AP test, whether from a little multiple choice problem where it might just be the velocity graph, right? Or maybe on an APC free response problem where they could ask you to do both parts. So I want to show you a few little tricks here that will help us do that. And that is that the curvy parts are hard, right? The curvy parts are when the slopes are changing. But there are linear parts to this graph. And of course, since this is a graph of position versus time, the instantaneous velocity is the slope of that position time graph. So what we're going to do here is we're going to break it down into the linear parts where the velocity, the slope, is constant. And then we're going to kind of connect the parts, all right, with the curvy parts here. And we'll talk about what that looks like on the velocity time graph. So first of all, for the first, it looks like about 2 seconds. Right? What's the slope of this graph, the velocity of it? Well, it looks like it pretty much just stands still, so the velocity is 0. See it down here? Now from 2 to 4, you can kind of look and see that the slope is getting steeper, which means the object's getting faster. But exactly, how do we draw that on here? Well, let's skip that part. Instead, let's focus on the next straight part, the next linear part, which I think goes from about 4 to 6 seconds. Right? This part right here is the linear part. Well, if I want to find the slope of that linear part, of course, I just use rise over run, which in this case is displacement over time. Right? Displacement over time is your velocity. What is the displacement? Be careful. If you're saying 4, you're not looking at the scale. It's actually 2, 4, 6, 8 meters, right, is the rise. And the run is, these are every one, so this is 2 seconds. So this person goes 8 meters in 2 seconds, which is better known as a constant 4 meters per second. Right? Be a little careful with the scaling. Seen too many people mess that up, right, and call this 1, 2, 3, 4 instead of 2, 4, 6, 8, right, and kind of get the problem wrong. So if he's going to go 4 meters per second, that's up here. But we have to start it where it is on this graph, right? That's why I draw them this way. Sometimes you'll see them side to side, but it's a little easier if you're drawing the kinematic stack of graphs because you can line up the time axes. So we're going to start here at 4 and go to 6 seconds at 4 meters per second. Right, there we go. So what's happening in between 2 and 4 seconds? Well, the slope is getting steeper, which means the velocity is increasing. So he's speeding up. So maybe we could draw something like that. Now, I drew it as a straight line with sharp corners. Is that really accurate? Maybe. It's kind of hard to tell. I mean, it's just a curve. Is it a perfect parabola or something like that? So, the AP is going to allow you to do this. Technically, you could draw this as a little like S curve, if you will, if you think of like a little S here. All right? You could draw it that way as well. That's a little more calculus-y, a little more realistic. All right? But a diagonal line will work just as well, really. Now, if we look up here, of course, what's it doing from 6 to 7 seconds? And then what's it doing afterwards? Well, afterwards, again, like the first 2 seconds, it stopped. So from 6 to 7, it's slowing down to 0, and then it stops for 2 seconds. So notice how I'm kind of mapping piece to piece from the position time graph down to the velocity time graph. if I'm given a function for this graph, I can do the calculus, right? But sometimes they give you a graph and want you to work with a little more complexity. So the next part here is we want to create the acceleration time graph. Hopefully you remember at this point that the acceleration is the slope of the velocity time graph. So we're going to do this again. We're going to kind of do it piecemeal. Right? For the first 2 seconds, the slope and therefore the acceleration is 0. It's actually not moving at all, right? So no acceleration. But from 2 to 4, well, if we're going to find the slope of this, right, we've got to do rise over run. The rise, be careful here, right? It's the change in the velocity over the change in the time. Change in velocity, change in time. Be careful, this is 4 meters per second as a rise and 2 seconds as a run. So it's 4 meters per second over 2 seconds for a grand total of positive 2 meters per second squared. So from 2 to 4 seconds, we're going to jump up to 2 meters per second squared. Note the dotted line connecting these two. That's because of how I chose to draw this graph. Since there's a sharp corner here, that's technically a discontinuity in the graph. In reality, you can't jump from one velocity to another without moving smoothly through the others, at least. Right? So we do the little discontinuity here with the dotted line just to make life nice. From 4 to 6 seconds, again, it's back down to 0. Right? There's no slope, so no acceleration. Again, note the dotted line to connect these up. From 6 to 7 seconds, well, now we do the same kind of rise over run. Be careful, we're starting here, going down, which makes it negative 4 meters per second of a change in velocity in 1 second only this time, for an acceleration of negative 4 meters per second squared. Note, positive velocity, negative acceleration means it's slowing down. And then the last 2 seconds, again, the velocity is the velocity is 0, so that means the acceleration is also going to be 0 because it's staying constant. So here's our kinematic stack of graphs. And again, the trick here was to realize you could kind of break it down by looking at the linear parts, right? Finding the slope of the linear parts and then kind of connecting them up. Okay. Now, a little bit of review here, some things that you've done in previous packets and worksheet. Right? So if the instantaneous velocity is the slope of this graph at any point, right? We could pick it anywhere, a curvy part, a linear part, right? Find the instantaneous velocity by finding the slope. We might also be concerned with, which is the derivative of the position function with respect to time in terms of calculus. And the acceleration is the slope of the velocity time graph, rise over run. Well, that in calculus would be the derivative of the velocity with respect to time. Remember, every slope is a derivative. Every derivative can be represented on a graph by a slope. So then, what's this notation you're asking down here? Okay, well, this is not a squared, and this is not a squared. This is Leibniz's notation for what is known as a second derivative. Basically means take 2 derivatives. Right? So if we start with a position function, we take 1 derivative to get to the velocity function, a second derivative to get to the acceleration function. You would read this as the second derivative of the position with respect to time. Don't forget the with respect to time part. That's what's on your horizontal axis, your independent variable, if you will. Right? So it's just the notation. You just got to get used to it. I don't know why the 2 goes in between on top and it goes to the right on the bottom. It just does. It's just the way how you write a second derivative. Technically, you could write third derivatives and fourth derivatives and fifth derivatives just by changing the exponents. Right? They don't always have physical meanings. There is technically a third derivative of the position with respect to time, the rate of change of acceleration, something called the jerk, because that's what happens to you when you change your acceleration. You know enough physics to know that to change your acceleration, we have to change the net force. So if you can imagine being pulled at a constant acceleration and then all of a sudden they want a faster acceleration, well, what are they going to have to do? They're going to have to jerk you, right, to get you to accelerate faster. So it's called a jerk. Doesn't pop up in APC, but technically exists. Past a third derivative, I'm not even sure if a fourth or fifth derivative would even have any meaning physically. So, now a little review thing. If the instantaneous velocity is the slope of the position time graph, don't forget, we can also find an average velocity, which is displacement over time. Notice the extra little line here for average. You might sometimes see like AVG or something for a subscript. And don't forget, we defined it as the slope of a line connecting any 2 points on this position time graph. For example, we could draw a line from 0 time, 0, negative 3 meters, up to here after 9 seconds. Find the slope of that straight line, and that would be the average velocity over the entire 9 seconds. Rise over run. Likewise, we could do a similar thing with acceleration. Acceleration is the slope of the velocity time graph. Well, the average acceleration, notice the extra line, change in velocity over change in the time, is the slope of a line connecting any 2 points on a velocity time graph. Now this one kind of gets interesting. If we connect the 0, 0 point all the way over to 9 seconds, note, what slope is that? It's got a 0 slope. It's a horizontal line. So the average velocity over the entire, the average acceleration over the entire 9 seconds is actually 0. Do you see that on the acceleration time graph? Well, look, we go at an acceleration of 2 meters per second squared for 2 seconds, and we go for an acceleration of negative 4 meters per second squared for 1 second, and those two things cancel each other out. Right? See how the areas under the curve kind of tell us the change in the velocity? Area under the curve here tells us the displacement. Area under the curve here, change in velocity. And since these are the same areas but opposite, they cancel out. Everything is logical. Everything has meaning. Right? They're just kind of more and more abstract models of reality. Right? The reality is the guy moving back and forth. They're actually moving in one direction in this case, standing still, speeding up, moving constantly, slowing down and stopping, right? All while going in the positive direction. But these are all a little bit more abstract, and the math is perhaps even more abstract, but they should all fit together logically. Okay, let's do an example here where we're going to actually use the calculus. Let's say we got an object moving in one-dimensional motion with a position function given by 2t cubed plus 3. Now, yes, there are units on this. I just chose to ignore them at the moment. Sometimes they'll do that on an AP test. Sometimes they'll put the units here, right on the numbers. Sometimes they'll list the units out. They'll say something like this statement, where the units are in meters per second cubed and meters. Those would have to be the units so that the position ends up in meters, right? So the time cubed cancels out with the seconds cubed. Right? So they might just list them out. But in this case, here's our position, little function notation over here. So I want to know several things. First off, I want to know the instantaneous velocity at 1 second and 2 seconds. Well, last year this would have been a little tough. But with the calculus, we know that the instantaneous velocity is simply the derivative of the position function with respect to time, which means it's the derivative of 2t cubed plus 3. Now, I did write out some steps, but if you can do it, feel free to skip steps as you get better at this. Like I said yesterday, if you're in first year calculus, by the end of the semester, you'll be skipping steps. So here is the derivative of a sum is the sum of the derivatives. We take the derivative of each piece one at a time. Over here, we multiply by the exponent, subtract 1 from the exponent. Here we have the derivative of a constant, which is, of course, 0. And it has no rate of change. So we end up with 6t squared. Multiply by the exponent, subtract 1 from the exponent. If you're not sure what I'm doing there, look up the power rule from yesterday. So now that we know the velocity function, well, really, this question is pretty trivial. We evaluate it at 1 second, we get 6 meters per second. We evaluate it at 2 seconds, we get 24 meters per second. There you are. So this part is really just, math, but this part is the beautiful part. This is the calculus approach to doing physics. Part B, what's the instantaneous acceleration at 1 and 2 seconds? Well, again, this would be a little tough if we were doing this graphically. We'd have to create a velocity time graph and then find the slope on the velocity time graph at 1 second and at 2 seconds to find the instantaneous acceleration. But with the calculus, we just take another derivative, because the acceleration is the derivative of the velocity with respect to time. From the last part, we know that the velocity function is 6.0 t squared. Power rule, multiply by the exponent, subtract 1 from the exponent. And so we get an acceleration function of 12t. Note, this is not uniformly accelerated motion. Kinematic equations would not apply to this problem, right? But the calculus does, right? As we have a dependence on time. Now, it's not a very complex acceleration. It's changing, but it's changing constantly because it's just a t. Not a t squared or a square root of t or something more complex. So, just like before, really the answer to the question is trivial. We plug in 1 second, we get an acceleration of 12 meters per second squared. We plug in 2 seconds, we get an acceleration of 24 meters per second squared. Okay with the calculus? All right. The next part is I want to find the average velocity and the average acceleration from 1 to 2 seconds. Right, so we just found the instantaneous values at 1 second and at 2 seconds. Now I want to know what was the average values during 1 to 2 seconds. Graphically, these would be the slopes of the line connecting any 2 points on the position time graph for the average velocity, on the velocity time graph for the average acceleration. But we don't have graphs, so we're going to do this mathematically. So as we just reviewed, the average velocity is the displacement over the time. Well, the displacement is, of course, final minus initial position. And that means we need to know the position at 2 seconds minus the position at 1 second. And the change in the time would just be 2 minus 1 seconds, right? Final minus initial. This is function notation up here, right? So we have to use this function now to calculate the position at 2 and the position at 1. Could you do this off to the side somewhere and plug the numbers in? Sure, right, if that's more comfortable. You know me, I like to work in one line, right? So kind of stepping up your math here in APC. If we plug in 2 seconds into the function, we get 2 times 2 cubed plus 3, minus at 1 second, which is 2 times 1 cubed plus 3. If we work that all out, that's what? That's 8 times 2 is 16, plus 3 is 19. 2 times 1 cubed is 2, plus 3 is 5. 19 minus 5 is 14 meters per second. So that's our average velocity. Doesn't tell you how fast we were going at 1 second or at 2 seconds. It tells you the average in between. Now, some of you might have been saying, why did we do all this work? Why didn't we just go back to part A, take our velocity at 1 second and our velocity at 2 seconds and find the average? In other words, why didn't we just add them up and divide by 2? But look what you get when you do that. 6 plus 24 divided by 2 is 15. That's not the answer we got here. Well, this has to be right. I mean, this is the math, right? So why isn't that right? Why isn't it right to add these two together and divide by 2? Well, the key here is the complexity of the function, and in particular, the complexity of the acceleration. All right? This thing is not moving at a uniform acceleration. It's speeding up, but it's speeding up faster and faster. So if you think about it, it's going to spend more of that second at lower velocities than it will at higher, faster velocities. You with me? Because its acceleration is increasing. And that's why the average actually ends up being a little bit below the simple average of adding and dividing by 2. Right? Now, if you would have just done that, you would have gotten the answer wrong, right? It's a common mistake on this kind of question on an AP test, right? Is that they just want to do it as fast as possible. So they go, oh, great. And they kind of led you into thinking that by making you do this part first. The equation will never steer you wrong, right? It takes into account how complex the position function is, how complex the motion is in doing this, right? Whereas the simple average doesn't. I know, a little tricky. Right? So the simple average isn't the actual average velocity, right? The velocity function's nonlinear. The rate of change of the velocity is non-constant. Another way of saying that, of course, is the acceleration is non-constant. Remember, it was a function of time. Average acceleration, well, again, let's use the equation. Average acceleration is change in velocity over change in time. Well, we actually know the velocity at 2 seconds and 1 second. Right? We just were talking about them, so we can just plug in the numbers. 24 minus 6 is 18 over 1 second. Right? We get an average acceleration of 18 meters per second squared. Now note, this is the simple average of our two accelerations here. 12 plus 24 is 36 divided by 2 is 18. So why did it work here? Because of the simplicity of the acceleration. Yes, the acceleration was changing, but it was changing in a linear way. It was spending, if you will, just as much time at the lower accelerations as it was at the higher accelerations. And therefore, the average is the one right in the middle. Right? It works because it's a linear acceleration, linear function of time, whereas the velocity didn't. If you're really good with your number sense and your idea of what these equations mean, right, sometimes you can do these problems a little bit more quickly, but remember, these equations never steer you wrong. Right? They will work all the time, whether it's a complex function or a simpler function. Hope you enjoyed our little discussion of derivatives and average velocities and accelerations. Oh, this is the simple average.